I will start in 3 minutes. Okay, it's 5:01 currently. I'll be starting now. And anyway, one student has joined. That is sufficient for me. So yeah, welcome to the week 9 live session. Welcome to the week 9 live session of uh, the NPTEL course NOC24 EE-143 tutorial. The course is titled Semiconductor Devices and Circuits, and it is taught by the instructor Professor Sanjeev Sambandhan from IIC Bangalore. I'll be the TA for this session as usual. My name is Yavar, and the schedule for these sessions is every Sunday 5 p.m. to 7 p.m. This is the email ID and the website. You can have a look, and I mean you can post queries there as well. So now quickly hovering over through the guidelines. Uh, In case you have any query, you can either raise your hand or you can ask in the chat window. Please ensure that your microphones are muted, especially when you don't intend to speak. Uh, and I would appreciate your cooperation in making this session an interactive one, because that is the purpose of this live interactive session. Um, I request you all to keep pen and paper handy along with a calculator, because that would, I mean, come handy for calculations that would be needed in the problems, right? So yeah, then the session recording link and the lecture notes, they will be shared by the NPTEL course team in the due course of time, of course. And uh, prerequisites, as usual, include the last week's lectures that covered the following topics: MOSFET, its introduction and IV characteristics, the subthreshold swing was discussed, right? And some additional concepts were also discussed. So, does anyone have any doubt? I mean, with regards to the last week's lectures? Okay, I'll take that as a no. So now we'll move to the first problem, right, for the today's session, which is following. So our designer wants your advice on discharging a 1 microfarad capacitor in his PCB, right, from 3 volts to 1 volt. He also proposes two different methods for the same, and let's investigate them both, right? The method 1 is an exponential discharge in 550 microseconds, and the method 2 is a linear discharge in 1 millisecond time interval. So it is recommended to clearly read conditions for the MOSFET operation in saturation, linear, and deep triode and cutoff regions to solve the next questions. Okay, leave that aside. For exponential discharge, let's say I now give you a MOSFET with mobility mu n, right? This is mu n. This mu n is 1000 centimeter square per volt second. The oxide capacitance Cox is 0.5 microfarad per centimeter square, right? This is your Cox by area, right? I mean, we usually denote such capacitances by this prime, right? This is per unit area capacitances. So this is Cox prime, the capacitance per unit area. And the aspect ratio that is given as 10, W by L is 10. Threshold voltage is 1 volt. So what is the value of the gate voltage to be applied? Does anyone have any idea how should we proceed this question? I'll give you some time, right? I'll wait for 3 minutes and then I'll do it myself if anyone is not able to do it. Before that, can anyone among you confirm if I'm audible? Just type yes or just unmute yourself and say yes, you are audible.
You're audible, sir.
Okay, fine, fine. Thank you. Okay, so you have your 3 minutes. Attempt this question, okay? I guess that was sufficient time for you all to attempt this problem yourself. Now, those of you who are already, solving this problem may continue, and I'll also do it at my own end. Fine. So now, uh, this is of interest, right? For exponential discharge, mobility is provided, Cox prime is provided, aspect ratio is provided, threshold voltage is provided, and we need to find the value of the, gate voltage. So now, your MOSFET has to behave like a resistor, right? For this exponential discharge. I'll write that. Has to behave like a resistor for exponential discharge. Right. I mean, your RC, right? So you need to bias this MOSFET in deep triode region, right? So your MOSFET um, has to be biased in your this deep triode region. Deep triode region. Your resistor behavior is independent of VDS, right there. Now, your R that is equal to 1 by mu n Cox W over L, your VGS minus VTH. Right, this is your R. And if you put in the values, you'll get it as follows. This would be your 200 by VG minus 1, right? Your VTH is 1, and turns out this factor is 1 by 200, so that's why I took it into the numerator. So right, remember this. Our R is this. Now, what is your, discharging equation, right? If it's an exponential discharge, it would be following. This would be your V of t. Your V of t would be your V of 0 exponential of minus t by RC, right? And your V of 0 is your 3, right? So you can write your um, okay. Okay, it's 3 volt to 1 volt, right? So Fine. So your 1 would be equal to 3 times your e to the power minus t by RC. So that implies that your, what should I say, R, that is equal to T. Your R, that is equal to T by C ln of 3, isn't it? Right, just work it out. It should be this, right? Because the exponential of, I mean, if you take this here and this would be e to the power t by RC, that is 3. And from there, this easily follows. So yeah, R is T by C ln of 3, and the capacitor is a 1 microfarad cap, and your R is this, right? So we are good to go. We'll write 200 whole divided by Vg minus 1 equal to your uh, T, right? And what is T? It drops to 1 volt in this time interval, right? 50 microsecond. So I'll write 50 into 10 to the power minus 6 whole divided by your Vg minus, sorry, your C. What is C? C is 1 microfarad. So I'll write 10 to the power minus 6 into your ln of 3, right? And from there, it's, I mean, straightforward. Some algebraic manipulations and you'll get Vg equal to 1 plus 4 ln of 3, right? Which will give you Vg as your 5.394 volts. Is it clear? Does anyone have any doubt on how we proceeded for this question? Okay, I'll assume no one has any doubt. So we'll move ahead. So now for linear discharge, right? Say we use the same MOSFET as in question 1. What is the gate voltage required for linear discharge? See, we dealt with this one. Now we are interested in this method too, linear discharge in 1 millisecond. So now, firstly, we need to decide, I mean, where we need to bias the MOSFET for this operation. And only then would we be able to, I mean, compute the value of the VG, right? So I'll write following. So your MOSFET has to behave like a current sink. Right? For sorry. I mean, it has to behave like a current sink for the linear discharge, right? And for this, your MOSFET has to be biased. in saturation region. Fine. So what do we have then? We have I is equal to C dVc by dt, right? And that is equal to C delta Vc by delta t. What does that imply? In saturation region, we have following equation, right? Mu n Cox by 2, your W by L, and then your VGS minus VTH whole square, right? That is your C delta Vc by delta t. This implies if you solve it for Vg, it turns out this would be VTH plus your square root of your this 2C delta Vc whole divided by mu n Cox W by L your delta t, right? And this implies that your Vg is equal to 1 plus your square root of your 2 into 10 to the power minus 6 into your delta Vc, which is 2, and then mu n is 1000, Cox is 0.5 into 10 to the power minus 6 times your W by L is 10, and uh, what is the duration in which that happens? It's 1 millisecond, right? So you're right, 10 to the power minus 3. Sorry. Yeah, 10 to the power minus 3. So work this out and you'll get this as your 1 plus square root of 0.8, right? And then that Vg is 1.8944 volts. Right? This is your Vg, 1.8944 volts. So that finishes your second question. Now, third one, right? For third, I would want you all to try this one out before I'll show it. Firstly, is everyone fine with the solution for the problem 2 that we did? Any doubt, or is this fine? Okay, I'll assume everyone is fine with that and no one has any problem. So we can move ahead to the third one then. So now for the MOSFET characteristic that is shown in the figure, the values of the linear region threshold voltage Vt and the MOSFET unscaled process parameter beta n, that is equal to mu n Cox is. Okay, so you need to determine both the Vt and this beta n, unscaled process parameter. Fine, and the characteristic is shown in the figure, right? You can refer to the figure and compute these two quantities. So you need to, uh, choose the correct option among the four. Right, I'll wait for you guys to attempt this one yourself first before showing it myself.
ക്ലാസ് നമുക്കല്ലാത്ത മാതിരി നിൽക്കണം.
Was anyone speaking something? Okay, I'll assume no. So yeah, I hope that was sufficient time for you all to attempt this problem. Sorry. Now we have this, we'll proceed this as follows. Right. We'll write with assumption that, I mean, your VDS is small in the linear region, and so is your this VDS square. So our equation for the IDS simplifies to following, right? Should I write that? Yeah, I mean, I mentioned that that is sufficient. The idea is VDS is small, right? Assuming VDS is small, you can write following. You can write your IDS that is equal to Kn, your W by L, and then your this VGS minus VT times your VDS. Is that clear? Now, we need to find VT and this, whatever you call this, beta n or Kn. So for that, we'll write two equations from this plot, right? Corresponding to VGS1 equal to 5, this, and this. So what are those two equations? Your ID, say ID1, that is equal to your Kn. I mean, I'm using Kn for this beta, you know, right? This is mu and Cox. So this is Kn, your W by L, your VGS minus VT, your VDS1, your ID2, that is equal to Kn, W by L. In fact, I should write here VGS1, right? And here I'll use VGS2. VT would anyways be same, and then this would be your VDS2, right? Then if we divide these two equations, I'll get following. I'll get ID1 by ID2, that is equal to your VGS1 minus VT times your VDS1 whole divided by your VGS2 minus VT times your VDS2. So then, yeah, once you do that, then I know following, wait, yeah, let's write on a different page. Adding a page, adding a page. Where is the different page? This one is better, right? So yeah, our VGS1, our VGS1 is 5 volt. Your VDS1 is your 0.25 volt. Your ID1 is 0.6 milliamps, right? Similarly, your VGS2, I chose that as 4, corresponding to VDS, this, what do we call this? VDS2, which is also 0.25, and your ID2, that is equal to your 0.4 milliamps. Then if I plug these values, I'll get 0.6 by 0.4. I mean, I'm plugging the values in this equation. This would be 0.6 by 0.4. That is equal to your VGS1 minus VT. That is your 5 minus 1, sorry, 5 minus VT. VT is something that we need to compute. And your 4 minus VT. And of course, there is this 0.25 and 0.25, which will cancel out, right? What else? Then we can solve this for VT, right? If we solve this for VT, you'll get following. If you solve for VT, uh, you'll get this equation. 0.2 VT, that is equal to 0.24 minus 0.20. Uh, since I wrote in the guidelines, I'm assuming you have pen and paper handy. So you can work this out. How do we reach from this to this? Pretty straightforward. I won't waste time on that. Then your VT would be your VT would be 0.2 volts, right? That is your VT. Now, the part two of the problem, because not only did we need this VT, we also need to find this unscaled process parameter, right? Beta n or kn, whatever you say, this one. So for that, we'll take one of these two equations, either this or this, and then plug the value of Vt and obtain the kn, right? We do this as follows. So I'll use this equation. Uh, let this be 1 and let this be 2. I'll write from 1. From 1 we have ID1, that is equal to Kn W by L. Then your VGS1, right? Quotient. VGS1 minus VT times VDS1. This part, right? And what is your ID1? Your ID1 is equal to 0.6 milliamps, right? So you'll write 0.6 into 10 to the power minus 3. That is equal to your Kn. Your W by L is probably W by L is. Do we have W by L? Take that as 100 by 2. Okay. Okay. I'm using W by I'm using following. Use W by L equal to 100 by 2. So then VGS1 minus VT. VGS1 is 5 minus VT. And what is VT? VT is 0.2. So this is 5 minus 0.2 times your VDS1, which is 0.25, right? And you can figure this out. Your Kn would be equal to your 0.6 into 10 to the power minus 3 whole divided by your this 50 into your what should we call this? This would be 4.8, right? Isn't it? Just double check this, okay? So this gives us Kn as 0.01, right? So we have Kn, we have Vt. That effectively solves the question, right? Because so this is 0. What will be the answer? The answer would be your this one, right? This is your Kn and this is your Vt, right? Is this okay? Somebody has a question. Yeah, please go ahead and unmute yourself, Ramaya.
So in this numerical, how did we find out ID1 and ID2 values?
ID1 and ID2 values, you were supposed to obtain them from the plot. I agree, the plot is not that clear. I mean, it should have been more readable, the values, but you may assume that if you'll get a question, a similar question in exams, that would be much, much better readable than this one. Does that answer your
Okay.
question? I agree,
Yes, sir.
this
But
is not
we have
readable.
selected a specific value of VDS, right? Yeah.
Yeah, you need to select certain value of VDS, right? Also because you were supposed to, I mean, we had to compute this, right, in the linear region. So
Linear
VDS
region.
was supposed to be lying somewhere in the linear region. And other thing that's obvious is you need to I mean, you had to do both the calculations at a particular value of VDS, right? So that, I mean, VDS, I mean, it was up to you, but the thing is, it should have been in the linear region.
Okay, sir. So
Fine.
that means
Does that answer?
before saturation is reached, that
Yeah, yeah, yeah.
particular VGS value should
Before
be
the
taken.
saturation is reached. Yeah.
Okay.
And before the saturation is reached for both the VGS values, right? For this one as well as this one,
Yes, sir.
right? Because for this one, the saturation would reach earlier, right? VGS minus VTH.
Yes.
I hope that's clear.
Clear, sir.
Okay, fine. Thank you. Does anyone else has any question? Yeah, I'll assume no one has any other question. So we'll move on to the fourth one then, right? So the question fourth is as follows. You will be given, I mean, two identical MOSFETs that are connected in the fashion as shown. Which among the following statements are true regarding M1 and M2? Uh, please attempt this one, right? Again, I'll give you some time. It's better to attempt the problem yourself before I show it. Attempt this. I'll wait for a couple of minutes. Okay. Was anyone able to answer this one? Sorry. Let's go through this problem. So, the MOSFETs are in series, right? M1 and M2 are in series, and we have been given these voltage, right? This 5 volt, this 3 volt, and this is grounded. And we are then asked to comment on the operating regions of M1 and M2, right? This is essentially the question. So, uh, what we can do is, uh, since these options, they don't mention anything about the MOSFETs being in cutoff. So what we can do is we can assume that the VT is less than 5. This is what we will assume. So we'll assume your VT is less than 5 volt, right? Since these M1 and M2 are identical, right? It's already written that they are identical MOSFETs, and they are in series, of course. So the currents should be same, right? The current flowing through M1 should be equal to the current flowing in M2, right? So let me write that down. Since your M1 and M2 are in series, so your ID1 is equal to your ID2. Fine. So now let's test each and every options one by one, right? Firstly, we'll have option 1. So in option one says that both the M1 and M2 they operate in saturation region. So if that is the case, what we'll do is we'll use the equation for the current in the saturation region for both ID1 and ID2 and equate that, and from there on uh, we'll see if that makes sense. If it's, I mean, if that makes sense or not. Let's write now. You're both M1 and M2, they are in saturation. So I'll write your beta by 2, your VGS1 minus VT squared, that is equal to your beta by 2, your VG, just a second. It's fine. Your VG is 2 minus VT, right? I can write this one. Then I can write following. Then I can write uh, 3 minus Vx minus Vt squared is equal to 3 minus Vt squared. Right? Why? Because for the M1, this is the VGS is sorry 3 minus Vx, and for our M2, this VGS is 3 volts, right? Straightforward, right? For this one, it's this voltage minus this voltage, which is 3 minus Vx, and for M2, this is this 3 minus 0, that is 3. That's why I wrote this. Now, what does this imply? If this is equal to this, then that means, what does that imply? Can anyone, I mean, comment on Vx? What should Vx be if this is the case? This is simple, right? Vx should be 0, right? Vx has to be 0 for this equation to be satisfied. So I'll write Vx is equal to 0, right? If now Vx is 0, what about VDS2? Right? What about VDS in this? That is 0, right? Because VDS2 is your Vx. So if Vx is 0, then your VDS2 is 0, right? So I'll write this means your VDS2 is 0, right? But now, what can you say about M2? I would appreciate if someone joins me in the discussion. Now, both M1 and M2 operate in saturation region. We started with that. Now, we got VDS2 as 0 volt. But for M2 to operate in saturation region, what is the condition that we need? That our
VDS2 should
VDS,
be greater than or equal to VGS minus 50.
yeah, exactly.
But
So,
that's not the case. So that means
but
it
that
could
is
be
not
in
the case.
VGS
So M2 is not in saturation, right? I mean,
saturation.
in other words, this is violated, right? That is
Yes.
my point essentially. So let me
So
still write it
why didn't
down.
the current, why didn't we take W by L on either side?
I mean, W by L on the other side, that would cancel out. So it's
Okay,
kind of
both are
same
of the
thing.
same size.
Club that, yeah, they are identical MOSFETs. It's written
Identical.
that
Okay.
they are identical MOSFETs. That is the reason I was able to do so. Yeah, you have a point. If these MOSFETs were not identical, then I should have taken W by L on both sides. So I'm clubbing all those factors into beta. That
Okay.
is the reason I'm able to do so because the MOSFETs are identical. So let me write what he just said. So your VGS2 minus VT, that is less than your VDS2, right? But this is the case for saturation, right? But this is violated, which implies, I mean, in other words, M2 is not in saturation, right? M2 is not in saturation. That's it. Now let me, so in other words, this is, I mean, incorrect option, right? So we'll proceed one by one. So now the other page. Now we need to explore the option, second option, right? Option B, which is now both M1 and M2, they operate in linear region. So let me write this. Both M1 and M2 operate in linear region. Now, if that is the case, which equation should I use? Or do I need to use equation at all? What can you comment on M1? Is it in saturation? For M1 to be in saturation, this is what we needed, right? I guess I should write that. For M1 to be in, I mean, I'm going against this option, but if I'm able to prove that M1 is in saturation, then by default, this option is incorrect. That is what my goal is. For M1 to be in this saturation region, this VDS1 should be greater than your VGS1 minus VT. But is that the case? What is your VGS1 there? Their VGS is, see, what is VGS1? Let me use this one. VGS1 is 3 minus Vx, right? This is 3 minus Vx. What about VT? VT is, I mean, less than 5, right? We, so I guess I can take any value, say, let me use this 4.8, okay? If my VDS is greater than this, then I'm good to go. But what is VDS1? VDS1, can anyone comment what is VDS1 for this MOSFET? Drain, VD minus VS, that is VDS1, right? So what is that? This minus this.
5 minus V.
5 minus Vx, yeah. So this would be 5 minus Vx. So now Vx goes. So I'm left with 5 is greater than 3 minus 4.8. Does that make sense? It does, right? 5 will always be greater than 3 minus a quantity that is less or equal to 5. Does this make sense, or should I mean, explain more?
It makes sense, sir.
Yeah, it makes sense, right? So I can write that M1 is in saturation. Right, M1 is in saturation. For this one, I'm confirm. I mean, I did not even use a linearity condition and then concluded on the nature of operating region. This is, I mean, something, this part is something that directly follows from the given bias conditions, right? So this one is sure shot. So M1 has to be in saturation. So this cannot be, this cannot be. So we are only left with this one, right? Where M1 operates in saturation region and M2 operates in linear region, but we still need to see if M2 actually operates in linear region or not. For M1, we are confirmed, right? The only thing, so I'll write. So I'll hope you will agree that I'll discard 3 options, but still I need to confirm if fourth one is correct or not. C, discarded. Uh, discarded. This one is also discarded. Now what about option D? In option D, uh, anyone, I mean, any idea how should we proceed now? In order for option D to be correct, what do we need to show? We need to show that M2 operates in linear region and M1 operates in saturation region. For that, what do I need to prove? I want you to answer this because that way you will understand this better. Ramaya, any idea? How should we proceed?
No, sir.
Remember we said that, sorry, we said that since these are in series, the current should be equal.
Yeah, yes, sir.
So for one, I'll use the current equation in saturation region, and for the other, I'll use the current equation in the linear region. And if from there on I get a condition that makes sense, then I'm good to go, right? So that is
Oh,
essentially the recipe. So we proceed as follows. So now M1 in saturation, your M2 in linear, right? And the equation that you get is your beta by 2. Wait, this would be VGS minus VTH whole square. Yeah, this is in saturation, right? So I need to use VD sat square. So this is 3 minus Vx minus Vt squared. That is equal to beta by 2. Here I have 3 minus Vt times Vx minus Vx square by 2, right? Because for M2, for M2 VDS is Vx, right? Vx minus 0 is Vx, that's why. So if you proceed, uh, you can take realistic values of Vx and Vt and convince yourself that this makes sense. Okay. I mean, you can take some examples to, I mean, convince yourself, but do this as an exercise. Okay. Your exercise is to convince that uh, this equation I mean this equation makes sense for your realistic values of your Vx and Vt. Fine, this is left as an exercise for you. And once you do that, option D is the right option. The other way to look at this is we discarded three options, so the only correct option left would be option D. And even in option D, the equation that we wrote, you can try values of Vx and Vt. What will be the values of Vt that you would choose? Anything that is less than 5 volt is a realistic value for Vt because we assumed that Vt is less than 5 volt. Okay, I'll leave this one now. What about this one? Question number 5. I mean, first, is this fine? Question number 4. Does anyone have any doubt in question 4? Anything? I'll assume no
Sir,
one has. Yeah, please go ahead.
we assume that VT is less than 5 volt. Is it because VT should be less than the maximum voltage in the circuit?
VT has to be less than 5 volt. The reason I did so is because I mean the options didn't mention about the MOSFETs being in the cutoff region, right? So you can assume that VT is less than this 5 volt VDD.
Okay,
Had the other thing been, if the cutoff region would have come into the picture or in the options, then I wouldn't have been able to use this assumption. Then probably this VT would have been given. I can say that way. Fine.
fine.
Okay. So now in the circuit, this circuit, M1 and M2, they are two identical MOSFETs, right? Again, the MOSFETs are identical and the MOSFETs are in series. This is actually the same one, right? Yeah, this is identical. Problem. So the acceptable value of the node voltage Vx is okay. So now you need to compute the value of the node voltage Vx. Please attempt this one. I'll wait for a couple of minutes if uh, even if you are not able to solve it, if you are able to come up with an approach on how to approach this problem, that is sufficient. I'll be fine with that as well. I'll just wait for 1 or 2 minutes. We already did the exercise of determining the operating regions of M1 and M2, right? So maybe you can use that as a starting point to approach this problem. I guess I should start, otherwise we'll get late. So this is what we concluded so far. M1 saturation, your M2 linear, right? And if you equate the two currents ID1 and ID2, what do you get? ID1 equal to ID2. Why am I equating? Because these are in series, right? In the series, the same current should flow through both the MOSFETs. So what is ID1? ID1 is your beta by 2, your VGS1 minus V2 T. Yeah, VT whole square, and that is equal to, wait, did I use beta here? It was beta, sorry, not beta by 2. So this is beta, and here this VG is 2 minus VT times Vx minus Vx square whole divided by 2. Right, this is the equation. So therefore your 3 minus Vx minus Vt whole square, that is equal to your 2 times your 3 minus Vt times your Vx minus your Vx square by 2. Now, how should we approach this one now? We reached this equation that is valid for this problem. Now, in the question, we are given that we need to find the acceptable value of Vx, but we are given 4 options. One way to approach this problem would be to literally try putting values of Vx, right? That is actually the most simplest one. I'll use the value 0.41 first in place of Vx, and what will I get if I use the value of Vx, which is the other unknown in the equation? It is Vt, right?
BT.
Vt, yeah. So I would, encourage you all to try. So we put, I'll write like this. A part, we put uh, Vx equal to 0.41, right, volts. And it turns out I'll get Vt as uh, roughly 1 volt, right? And uh, if I use Vx as 1.41 volt, I'll get a Vt that is complex, right? That has an imaginary part. So I cannot use this one. Wait, I should write this one so that you are able to follow. Part B, I put Vx is equal to 1.41 volt. What do I get? I get Vt minus 0.3 plus minus 1.94 J. Is this fine? Vt is equal to minus 0.3 plus minus J 1.94. Then if I use Vx as 2.41 volts, 2.39, I'll get an irrational number. So it turns out that for all the values of Vx apart from option A, I'll get unrealistic values of Vt. So the only option that gives a realistic value of Vt is Vx equal to 0.41 volts. So hence that is the correct option. Is this clear what I just said?
Yes, sir.
Okay. So that finishes our fifth one, and then we can move ahead to the sixth one. So in the circuit, Vd is doubled from 2 to 4 volts. Just a second. So your Vd is doubled from 2 to 4 volts. The ratio of the currents for the respective Vd, 2 volt to 4 volt, is You need to determine the ratio of the currents. For this, note your VD and VG are shorted, right? Your VGS is equal to your VDS, right? So if your VGS is equal to VDS, what is the operating region of the MOSFET? You guys must have read this one. If we short gate and drain, the MOSFET is in saturation, right? Will it be? Think about this if you don't know, I mean, or search it out. This is something that you should know.
Yes, sir. The train cannot go
Yeah,
below the gate.
it cannot breach below this. Yeah, correct. So I'll use, so the reason why I was interested in determining the operating region first was because I had to use the equations of the current, right? I had to take the ratio of the currents. So I'll use the saturation region equations. So I'll use the following. I'll write as your gate is connected to drain, your VGS is equal to your VDS, or I can say your MOSFET is in saturation, right? And uh, therefore, what is the ratio of the currents? Ratio of the currents, your ID1 by ID2, that is equal to your VGS1 2 minus 1 का square whole divided by 4 minus 1 का square, right? So I can write following. I can write this is equal to your 1 by 3 square, which is 1 by 9. So I can write ID1 is to ID2. This is equal to your 1 is to 9. Is this fine? So that is what I had to compute, right? VT was 1 volt, that was already given. So ID1 to ID2 is 1 is to 9. So this is the correct option. What about option 7? In the same question, right? Uh, when VD is changed from 2 volt to 4 volt, the current increases 16 times, right? So the increase in the current is 16 times. So the question is asking now to compute the value of VT if this is the case. Earlier, see, the difference between the two questions is earlier we were given VT and we were asked to compute the ratio of the currents. Now we are given the ratio of the currents and we are being asked to compute VT. Trivial question, right? Those of you who were following should be able to, I mean, answer this one easily. See, I'll write now, your VT is equal to your 1 by 3 square, which is 1 by 9. So I can write ID1 is to ID2 is 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So this is equal to your 1 is to 9. So your ID1 by ID2. What is that equal to? That is your 1 by 16. And that is equal to, it goes from 2 to 4, right? So this would be 2 minus Vt whole divided by 4 minus Vt square. 2 minus Vt whole divided by 4 minus Vt square. Right. So this implies I'll have 4 minus Vt equal to 4 times 2 minus Vt. I took square root, right? So what does this imply? This implies your 3 times Vt is equal to 4, which implies your Vt is 4 by 3. So this is what I can write. Your Vt is equal to 1.33 volts. Right, this is your Vt. Question number 7 done. Now, for the next 3 problems, I would prefer you take these 3 problems as an assignment. Okay. I mean, these are not the one, I mean, in your main assignment, but you can use them as a practice problem. Okay. These are not that difficult, but take them as homework for this live session. And if you're not able to solve these, you can get back to me and I'll provide you the solution. And if that solution is not enough, we can discuss over a meeting before the next live session. So that in the next live session, we are able to, I mean, we should be able to start the week 10 content. I mean, the live session corresponding, the problems corresponding to the week 10 content. Will that be fine?
Fine, sir.
Okay, so you have 3 problems, right? This 8, 9, and 10. So if, I mean, anyone has any query regarding today's live session, please, I mean, please speak up. And if no one has any doubt or no one has any query, we can probably wrap up the session right here. Should we then end the session if no one has any query?
No, sir.
Hmm?
Sir, I had a general doubt about
Yeah,
the
yeah,
transfer
please.
cara.
About the,
Transfer cara.
okay,
IDS versus
transfer
VGS.
IDS versus VGS, fine. What is
Yes,
the
sir.
doubt?
So, for varying VDS, as VDS increases, um, we see that the graph also rises up.
Yeah, and that goes as square, right? I mean, you're
Square.
probably talking about the ID SAT values, right? Those
Yes.
rise as square of VDS, true. But that is not true in general, right? I hope you know it,
Yeah.
right?
Partially we have linear relation.
No, I mean, for short channel devices, that is not true, right?
No, sir. I don't know that.
Okay, I mean, what was your question then? I probably shifted
My
this.
question is,
Hmm.
shouldn't the graph rise up at different values of VG? Because as VD increases, the
Hmm.
threshold value shouldn't remain the same, right?
Your threshold is independent of VD, right? Threshold is a process parameter that has nothing to do with the bias.
Okay.
Yeah.
No, I meant as VD increases,
Hmm.
the current should go non-zero. Current should we should see start seeing current only at different for higher values of VG, right? Only then we can nullify the pinch off.
Wait, you are saying I actually did not got your question. So see, this is probably what you are talking about, right? Sorry, this is IDVD.
Yeah.
You are talking about the transfer characteristics. So this is something like this, and then, right?
Yes.
So what is the doubt?
Um, my doubt is that for the suppose we have VD1 and VD2 where VD2 is greater than VD1
Okay.
and
Wait. I'll
yeah,
actually, so let me do it here. So you are saying that I'll have two curves. Uh, suppose this and this. I mean, ignore the scales. So you are saying that I'll have two VD values, right? VD1 and VD2.
yes.
Then,
No, the x-axis it's VG transfer current.
sorry. This is IDVG. My bad. So this is your VD2 and this is your VD1 where VD2 is greater than VD1. This is your VGS and this is your IDS. Yeah, now please continue with the question.
Yeah, for the case of VD2, we
For the
shouldn't
case of
see a current for the same value of VGS.
for the same value of VGS, you should see
VGS.
higher current, right? You should see higher current.
Uh, no, that's
Why
what
do you,
doesn't make sense to me.
why do you think that you should not have a higher current?
Because since you have a higher VDS
Hmm?
now,
Hmm?
uh, the the VGS that you used earlier wouldn't suffice to have a current, right? You need a higher VGS. Only then the pinch off would be cancelled off.
See, your
Since you
VD
have a higher
sat,
VDS, you have a pinch off earlier, right?
see, your VD sat is VGS minus VTH. Only if your VD is greater than this VGS minus VTH, you will have pinch off, right?
Yeah.
Then I actually was not able to get your question. You are saying that, could you rephrase your question again?
Um, for the if we had to take the plot for VD1,
VD1,
as we
fine.
sweep VGS,
As we
we see
sweep
that
VGS,
at a particular point the current starts going non-zero at a particular VGS.
fine. This one, for example, I mean, say this one, whatever.
Yes.
Hmm?
Now coming to VD2, the plot for VD2.
Hmm. This, okay, one more thing. This, okay, first continue with your question. Yeah. And then for
Okay.
VD2, yeah.
And then for VD2, since the drain source voltage is increased,
Hmm.
um, you'll have a pinch off earlier, right?
Since your this has increased, your pinch off would decrease. Yeah, pinch off would occur earlier.
Earlier. That
Okay.
means you need a higher gate source voltage to
Huh?
make the current flow, right?
Pinch off.
So that means the current should be, you shouldn't get a current for the same value of VGS that you got for the plot number one.
Okay. So you're saying that the point where this goes to non-zero for VD1 and the point where it goes for non-zero for VD2, those should be different. Is that your
Different.
question?
Yeah. I'm saying that VD2 plot should continue going zero for a longer time and then only it should rise.
VD2 should go for longer. I
Uh,
mean, zero for longer.
will zero for longer, yeah. And it should rise for a higher VGS only.
I'll think about it. Okay, I guess I need some time. I'm I'm a little tired right now, so that's why I'm not
Okay,
able to think over this.
fine.
I'll think and I'll probably email you either by tonight or tomorrow morning positively.
Okay, sir,
Fine, I
fine.
got your
Thank you.
question. I got your question.
Okay. I have even asked the
And
same doubt over the forum also.
okay, can you do one thing? Can you copy that and mail me that question? So
Okay, sir.
even if I forget, still I'll have that as a reminder. Fine, just copy. You have my email ID, right?
Yes, sir. I'll take it from the recording.
Yeah, you'll take it from the recording. Yeah. for this session, I guess. Now, for other students, you have these three assignment problems. I mean, the homework problems: 10, 9, and 8. Yeah,
Okay.
thank you. This was probably, I guess, the most interactive session that we had among all the 9 sessions that we had. And this is what I want. The sessions should be interactive, and because otherwise it really gets boring. To I mean, to be there for 1.5 hours or 2 hours without anyone interacting is a tough job, to be honest. So thank you, and we'll wrap this session here then. Okay. Thank you.
Thank you.
Bye.